Hello guys, welcome to Ramta Solutions. Today we are looking at Avogadro's number. This is the video that we promised you that we are going to offer you guys. Okay, so this video is only going to be based on questions using Avogadro's number. So before we proceed, a quick reminder. Remember we said n is equal to capital N over capital N subscript A, where this capital N was number of particles, right? And this N sub A was Avogadro's number, right? It was Avogadro's number. If you recall, Avogadro's number is 6,02 times 10 to the 23, okay, times 10 to the 23 particles per mole. Okay, that was Avogadro's number. This is the number of moles, right? This is the number of moles. Okay, all right. So we are going to have some questions where we are basically dealing with Avogadro's number. So, or rather using Avogadro's number. So let's start with example number 1. Example number 1 says, a sample contains 5 grams of zinc. Okay, a sample, oh boy, I don't know what's going on. A sample contains 5 moles, not 5 grams, 5 moles of zinc. The first question, what is the mass of the zinc in the sample? What is the mass of the zinc? Of the zinc in the sample? Question mark, of course. B, how many atoms of zinc are in the sample? How many atoms of zinc? Oh boy, that problem again. How many atoms of zinc are in the sample? Okay, so our solution, we are referring to zinc. So again, mass is, before I do that, let me remind you of that triangle. N equals M over mass star, and or capital M. So what is this? This is N equals small letter m over capital letter M. So we are looking for the mass, therefore we can say M equals N times capital M. Okay? Moving on. Our mass is, what is the number of moles? We have 5 moles of zinc. We have 5 moles of zinc. Now, we will get the relative atomic mass of zinc from our periodic table. When we look on the periodic table, zinc, let me look for it. It's Zn, it's 65. It's 65. Okay? So it's 65 grams per mole. Therefore, what is our mass? Our mass is 5 times 65 must be 625. I will confirm, I'm not sure. 565. Yeah, 565. Confirm. 5 times 65. Oh, no, it's 325 in fact. It's 325. Why did I go to 600? Yeah, it's 325. Yeah, it's 325. Okay. All right, so this is 325. Now, the second question said we must calculate the number of atoms of zinc that are in the sample. So you recall the equation was N equals capital N over capital N sub A. Guys, this equation, you get it in your formula sheet in your examinations. So we are looking for the number of particles. That will be N equals, capital N equals small letter n multiplied by Avogadro's number. What is this? The number of moles were 5. And what is Avogadro's number? 6,02 times 10 to the 23. So what is this? So this is 5 times 6,02 times 10 to the 23. Oh boy. Times 10 to the 23. It is 3,01. It's 3,01 times 10 to the 24. The question was saying we must calculate number of atoms. So it'll be, we will say the particles we're referring to are atoms. Okay, so 5 moles of zinc have 3,01 times 10 to the 24 atoms. Okay, all right, perfect. Now we are then going to number 2. Let's try number 2. We will look at a compound. Okay, for number 2, we will look at a compound. So number 2 says, how many oxygen atoms? How many oxygen atoms are in 0,25 mole of calcium nitrate? Okay, in calcium nitrate. Okay, so for this question, we are given the number of moles. We are, however, looking for the number of oxygen atoms. Okay, we are looking for the number of oxygen atoms. So when I do this, I want to extend Avogadro's number. Okay, I will say Avogadro's number is 6,02 times 10 to the 23 molecules. Okay, mole. Okay, now I'm going to show you why I am doing this. Remember, I was saying it's particles. Okay, particles, it could be atoms, could be molecules, could be whatever. But in this case, because we are indeed looking at a molecule, I will use molecule. Okay, now pay attention to what I will be showing you. We have already shown you that number of moles equals number of particles over Avogadro's number. And we can say number of particles equals number of moles multiplied by Avogadro's number. This is important. By virtue of writing this equation, you have a mark. Now, I need you guys to pay attention. Okay, I need you guys to pay attention. We are looking for number of oxygen atoms. Okay, we are looking for number of oxygen atoms. So if you like, you can extend this equation and say multiplied by all atoms, but I'm going to show you. So we will say, or maybe let me do this. You can say this is multiplied by all atoms per molecule. Okay, all atoms per molecule. So what we are going to do here is basically the beauty of maths. Okay, we are basically doing maths as well. Okay, we are doing maths as well. All right, so let me show you. I want to show you something that we call dimensional homogeneity. That says whenever you solve equations, the units must make sense. Okay, so let's see. The units that we expect for number of particles could be atoms, could be molecule, could be ions, could be whatever, but they must make sense. So you don't want to have units that are confusing. For example, if you are calculating number of moles, you should never get kilograms. Let me show you what I mean. So for this exercise, the number of moles given are 0.25, let me say, moles. Okay. And then you have Avogadro's number, which is 6.02 times 10 to the 23. Remember what I said to you. It'll be molecule per mole. All right. Now, because I'm saying per mole, okay, let this guy come back. Because I'm saying per mole, I'm going to write. Oh, he says I should wait. Why is he buffering now? Okay, let's wait, guys. But otherwise, if you are with me, you can just say molecule over mole and close the bracket. Okay, I'm going to write that. Okay, I'm back. So this is molecule per mole. And then you look at the compound or the molecule in question. For the molecule in question, we must ask ourselves, how many oxygen atoms do we have? When you look at it here, we have 1 carbon atom, 2 nitrogen atoms, and 3 times 2 oxygen atoms. So that tells you we have 6 oxygen atoms. So we will say this is multiplied by 6 atoms per molecule. So because I'm saying per, let me just do this. Per molecule. Okay. Now, let's see if indeed we will have atoms at the end. This cancels with this. This cancels with this. What are you left with? You are left with atoms. Now, let's get our answer. Let's get our answer. 0.25 times. Guys, remember, do not make a mistake here. Maybe let's do this. Let's call this O atoms. Okay, O atoms. Let me erase it because it looks like 60. So 6 O atoms. Okay, now that's better. 6.02 times 10 to the 23 multiplied by 6. What is our answer? Our answer is simply 9.03 times 10 to the 23 O atoms. Okay, this is 9.03 times 10 to the 23 O atoms. Okay, atoms. Happy? Perfect. I'm going to try another one, guys, that looks exactly like this one, but I'm going to change the question. Okay, so let's try another one. I'm going to say now number 3. What should I do? Okay, so what I'm going to do now, let me make it slightly different. Okay, how many hydrogen atoms, which is H atoms, how many hydrogen atoms are there in 5.1 grams of ammonia molecule? Okay, of ammonia molecule. So here, as you can see, to use Avogadro's number to calculate basically the number of particles, we need to first find the number of moles. Okay, so here we will say N equals M over this guy. Now recall, Mr. NH3 or molar mass of NH3 is, on your periodic table, relative atomic mass of nitrogen is 14 and that of hydrogen is 1. So this will be 17 gram per mole. Okay. So if you like, you can do what I'm going to do, or maybe let me just do it in a long way. So we will then say, what is our mass? Our mass is 5.1 grams. What is our molar mass? Our molar mass is 17 gram per mole. Per mole. Okay. Okay, so now let's get our answer. Getting our answer, 5.1 over 17 is 0.3. Okay, this is, oh boy, problem is starting again. It's 0.3 mole. Okay, so the number of moles of ammonia is 0.3 mole. Okay, so these are the number of moles of ammonia, or the number of moles of ammonia. Okay, perfect. Now, to find the number of hydrogen atoms, we will therefore say N equals N Avogadro's constant times O. Sorry, it's not O this time around, it's H. This time around, it's H atoms per molecule. All right, now let's go. The number of moles we got in this question was 0.3 moles. I'm going to put the values again so you get used to it, times Avogadro's number 6.02 times 10 to the 23 molecule per mole, or molecules per mole, and then how many H atoms are there on the ammonia molecule? We have 3 H atoms, so it'll be 3 times. Can you see that? It's 3. So it will be 3 H atoms over a molecule. Alright, so for an ammonia molecule, you have 3 H atoms. So let's see, what do we get? Multiplied by 6.02, 10 to the 23, multiplied by 3. Our answer is 5.42 times 10 to the 23 H atoms. Okay? H atoms. Okay. Perfect. Now, let's try method 2. So method 2, remember we said we know N equals M over mass over molar mass. Again, we know that number of particles equals number of moles multiplied by Avogadro's constant. All right? So this can basically be, because we said wherever we see number of moles, we see mass over mass over molar mass multiplied by Avogadro's number. Okay, so now let's answer this question just in one line. In one line, we will say number of moles is equal to number of particles is equal to mass over molar mass multiplied by Avogadro's number, then multiplied by H atoms, multiplied by H atoms per molecule. All right? So let's substitute. What we had was that the mass was 5.1 gram. I'm going to return it. And molar mass was 17 gram per mole. And Avogadro's number is 6.02 times 10 to the 23 molecules per mole. Then how many H atoms do we have? We have 3 H atoms per molecule of ammonia. So per molecule. I know when you look at this, you ask yourself, okay, will they cancel? Yes, they will cancel. I'm going to show you how. Gram cancels with gram, as you can see, per mole with mole. When bases are the same, you add exponents. So check this out. -1 plus 1 will be 0. So the moles are cancelling. Otherwise, this per mole is similar to writing it here and saying it's gram mole over gram. So obviously the moles will be cancelling. And then molecule cancels with molecule. What do you get? You still get 5. you still get 5,42 times 10 to the 23 H atoms. All right? You still get that, isn't it? All right. Okay. So I think you guys now have an idea of what you are doing. All right? You guys now have an idea of what you are doing. So let me try one last example. So it's example 4. It's example 4. So example 4, oh boy. Example 4 says, calculate the number. I think, should I try? No, I'm going to try for 5 examples. Calculate the number of carbon dioxide molecules. Okay, calculate the number of carbon dioxide molecules in 2,2 grams carbon dioxide. Okay, carbon dioxide. Okay. So let's see. We are looking for the number of molecules. So obviously it means we must calculate, and we are given the mass. Like I showed you, it's up to you how you do it. You can do it in one line, or you can do it step by step. Because I have shown you step by step, I think you guys now have an idea. But let me just show you step by step instead of one line. So we will begin by saying number of moles over is equal to mass over molar mass. Now when we look at master carbon dioxide, it is 12 plus 2 times 16. When I look at this is 32, it's 48 grams per mole. Right? It's 48 grams per mole. Isn't it? Yes. Is it 48? No. It's not 48. It's 44. It's 44. Yeah, it's 44. It's 44 grams per mole. Okay? Perfect. So, moving on. Number of moles is 2,2 grams over 44 gram per mole. What do you get? Let's see. Remember, guys, when you do this long procedure, do not round off. Okay, 2,2 over 44 is basically 0,05. This is what you are getting in your calculator. So luckily, I don't have to round it off in any way. So the number of moles is 0,05. Okay, we are good to go. Now, the number of particles is equal to number of moles multiplied by Avogadro's number. What is it? It is 0,05 mole or moles multiplied by 6,02 times 10 to the 23 molecules per Okay, let's see. Answer multiplied by 6,02 times 10 to the 23. Oh boy, what did I do? Times 10 to the 23. What do we get? We get 3,01. So we get 3,01 times 10 to the 22 carbon dioxide molecules. Okay, carbon dioxide molecules. Okay, carbon dioxide molecules. So let me see previously what we have done. Okay, all atoms, number 1. I said what were we looking at? We were looking at how many zinc atoms. Okay, so here you could have said zinc. Maybe let's fix it and say zinc atoms. So to be consistent, zinc atoms. Okay, we are fixing number 1. And then let's go. Now, all the others are okay. Now, let's try the 5th example. Okay, let's try the 5th example. So, example number 5, we'll say to calculate the mass of 1,806 times 10 to the 24 copper atoms. So what we need to do now is to ensure that we get the molar mass of copper, relative atomic mass of copper. Okay, we need to make sure that we get it. So let's look on our periodic table. Copper is atom number 29. So mass of copper, molar mass of copper is 63.5. 63.5 gram per mole. Okay, so with this one, guys, we have the number of particles. What we need is to basically get the mass. So we basically work in reverse. Recall, N equals, rather, number of moles equals number of particles over Avogadro's number. Now, what does it mean? Number of moles, or let me write going down. We have number of particles. We have 1,806 times 10 to the 24 copper atoms. Now, Avogadro's number, what will we say? We will say this is 6,02 times 10 to the 23 copper atoms per mole or per mole. Okay, now let's see. So let's get our answer. 1,806 times 10 to the 24 over 6,02 times 10 to the 23. What we get is we get 3 mole. So number of moles of copper are 3. So we get 3 moles of copper. Now, proceeding, we also know that number of moles is equal to mass over molar mass, right? What are we looking for? We are looking for mass. So we'll say mass is equal to number of moles times molar mass. Okay, so we said our number of moles, we had 3. Molar mass of copper was 63.5. 63.5. Maybe let me do this. I'm just writing units, guys, just to show you that indeed whatever that we're doing will yield the results that we're looking for. Okay, so this was 3 moles. Molar mass was 63.5 grams per mole. As you can see, the moles are cancelling. Hence, you will be left with, let's say, 3 times 63.5. Our answer is simply 190.5. 190.5. I like leaving it to 2 decimal places because your exam says you must always leave it to 2 decimal places unless stated otherwise. So this is 190.50 grams. As you can see, you are left with grams. Now this makes sense. Okay, this makes sense. You were expecting to have a symbol of gram. So normally, you don't have to write the SI units, guys, or the units. I'm just writing the units so you can see that whatever that you're doing is really making sense. Okay, and the units are also consistent. Okay, so with that being said, ours ends here, and I believe, guys, you will ace this. So with that being said, it's a wrap, and bye.